Hello, everyone. Today we'll get into how quantum computers actually compute. First, we'll see how numbers are stored in quantum computers, then discuss how a calculation can be performed with stored numbers. Let's start by talking about number representation and use the number 43 for demonstration. The decimal representation, i.e. base 10 of 43, is this. Notice how the digits 4 and 3 are coefficients multiplying powers of 10 in the sum. Similarly, the binary representation, i.e. base 2 of 43, is written this way, with terms involving powers of 2. The coefficients together make up the binary representation of 43, written as 101011, which is a 6-bit number. To store this in a quantum computer, we need to store each bit in 1 qubit, as can be seen by this ket representation. Or without the tensor symbols, the 6-qubit state is written more compactly this way. In order to store numbers, we will need the help of the bit flip gate, which flips ket 0 into ket 1 and vice versa. To store the number 43, we start with 6 qubits all initially in state ket 0. Then we apply the bit flip gate on the first qubit to change the state to ket 1. Then we do the same to qubit number 2. We don't need to flip qubit 3, so we leave it alone. Then flip qubit 4, leave qubit 5 alone, and finally flip qubit 6. This is the quantum circuit diagram for storing the binary representation for number 43. Since we're using 6 qubits, the compact way to draw this circuit is this. Notice the number 6. It is the binary representation of the number that's usually inside the ket, but you might encounter situations when the decimal representation is used instead. For 6 qubits, it might not seem necessary to represent this qubit bundle compactly, but it can be a mess if we're dealing with, say, 100 qubits. So generally speaking, if we have an L-bit number x with this binary representation where the coefficients are the binary digits, this is how the bundle of L qubits can be represented compactly. Now that we know how to store a number, the next question is how can we perform a calculation on it, such as finding the value of a function f of x? A first guess would be to transform the qubit bundle represented by ket x to ket f of x. But the problem with this is that it's not a reversible operation, and we need reversible unitary operations in quantum information. For example, a function such as sine of x equals 1 for many different values of x, so it does not have an inverse. Instead, to overcome this problem, we will have two different qubit bundles. One we refer to as the argument register, and the other the function register. The argument register stores the value of x, while the function register is where the value of f of x is stored. This is how we represent them as kets. The idea is to transform the combination ket x, ket y using the unitary u sub f into this. Notice that y is transformed into y plus with a circle f of x, which is the bitwise addition modulo 2 of y and f of x. We'll elaborate on that soon, but for now, note that the value of f of x is stored in the function register. This is the quantum circuit diagram that represents this operation, where the top qubit bundle corresponds to the argument register and the lower qubit bundle to the function register. Now let's elaborate on what we mean by bitwise addition modulo 2. It means performing an addition modulo 2 between two numbers bit by bit. But the question remains, what is addition modulo 2? It's the remainder that you get after adding two numbers and then dividing them by 2. For two 1-bit numbers, the sum is defined this way. Let's look at an example where we add two 6-bit numbers, bitwise modulo 2. 43, which has this binary representation, and 56 with this representation. Adding the first corresponding bits, we get 0. Then 1, 0, 0, 1, and finally 1. As an exercise, I would like you to consider the case when y and f of x represent 1 bit each, and you're free to consider all the different cases one at a time to show that the operation represented by u sub f, which we talked about, is reversible by showing that the bitwise addition modulo 2 of y, f of x, and f of x equals y. A bientôt!